array data models, and query languages. ArrayDBMS data models try to capture and generalize the diversity of big arrays, time series 1D arrays, two-dimensional geospatial grids, tracks, swaths, or other arrays where a dimension represents coordinates or time, height, model number, and so on. Three-dimensional spatio-temporal cubes like astronomical observations or biomedical data, unstructured meshes, and generally any data that can be modeled by multidimensional arrays. Arrays are traditionally stored in files, not databases. Such files have complex naming, diverse coordinate systems, formats, data types, and so on. For example, the same dataset may have very different storage layouts in different file formats. It's also important that a dataset is almost always split into multiple files. The most widely used industry-standard array data models are Unidata Common Data Model, GDAL Data Model, and the ISO model. They're mappable to each other to some extent. All of them pursue the same main goal: provide a uniform access to a data type that can be provided in different storage formats or service APIs. These models resulted from decades of considerable practical experience, but they share a key drawback. They work only with a single file, not with a set of files as a single array. However, a dataset is usually split into multiple files. The ChronosDB data model formalizes and generalizes industrial experience. In addition, it treats arrays in multiple files arbitrarily distributed over cluster nodes as a single array. Moreover, it has a rich set of data types and supports multiple file formats with proper abstraction. These features are not simultaneously present in other data models. Since GDAL, CDM, and other data models are mappable to the ChronosDB data model, let us cover the latter in more detail. ChronosDB manages multi-dimensional arrays. An array has a name, a set of coordinate arrays, and type T. Coordinate arrays can also have names. Coordinate arrays enable modeling a wide variety of data types. A coordinate array maps indices of an array axis to physical values. For example, the one-dimensional coordinate array named lat is of type double and with length 4. Its elements are degrees latitude. Alternatively, it's possible to define an array just by its shape. A hyperslab of an array is an ND subarray of this array. We'll need these definitions in the tutorial. The ChronosDB data model has two levels. A user perceives a large array at the highest level as a single object. A set of system-level arrays or subarrays is distributed among cluster nodes and stored as ordinary files in diverse file formats. An operation with an array is mapped to a sequence of operations with respective subarrays. In this example, array A resides on 3 cluster nodes. Subarrays are separated by hyperplanes and referred to by keys. For example, we refer to the highlighted subarray by the key -1, 0, and 1. This is the example of a ChronosDB array and its schema for real-world data. Red rectangles in the figure are subarrays. They are logically presented to a user as a single large array. The ChronosDB GDAL-info command prints array schema, the meaning of the fields, and this output is the same as the well-known GDAL-info tool that handles only one file at a time. As GDAL-info is quite popular, most users avoid learning a new array schema notation and inspect ChronosDB arrays in a way they are accustomed to. Let us take the real-world dataset from the previous slide. We would like to compute a popular vegetation index called NDVI. It takes two two-dimensional arrays as input and produces a single two-dimensional array as output. Array query languages greatly differ between array DBMSs. There is no well-established standard yet. ChronosDB users work with the system as if with already familiar command line tools. ChronosDB commands have the same names, syntax, and options as well-known command line tools, for example GDAL-calc. Hence, users can start working with ChronosDB immediately and avoid learning a new language. RAS-daemon query language, RASQL, strives to be similar to standard SQL, but some queries may look unusual for an SQL user. For example, is the query at the bottom. SciDB Array Functional Language, AFL, has a set of operators in the functional style. Nesting is used to feed the output of one operator to another operator, forming sometimes long operator chains. Here, apply takes an array produced by the join operator, and the store operator materializes the resulting attribute extracted by the project operator. PostGIS provides a lot of functions called from pure SQL. PostGIS users work with a set of independent 2D tiles, not treated as a single array. Users must explicitly seek intersecting tiles and properly organize the computations, which is quite tricky. Here, a predefined UDF computes NDVI. ArrayDBMS data models are at their early stages. They largely focus on numeric arrays and largely omit other important data types like polygons, tables, and graphs. Nowadays, a key meta challenge is the joint processing of diverse data types within a single system, ArrayDBMS. Let me showcase several promising R&D opportunities. One of the ways to solve the challenge is the algorithmic way. As an example, consider Raptor. To compute zonal statistics, like average of raster values within a polygon, existing systems rasterize the polygon or perform point and polygon tests. Both approaches are time-consuming. Raptor uses scan lines with a step equal to the cell size. It quickly computes the range of indexes that contribute to the result. However, Raptor is designed for zonal statistics, so much more operators are required. Polystar systems tackle the challenge in another way. They do consider ArrayDBMSs as their components but underutilize them. For example, geospatial, bioinformatics, astronomical, and other array-intensive workloads have been not extensively studied in Polystars. I encourage you to explore this interesting direction. ArrayDBMSs can potentially model graphs and tuples as arrays, but we didn't extensively evaluate that. We would like to keep users within a single system during array-intensive workloads. Otherwise, we miss both users and optimization opportunities. Modern ArrayDBMSs do not implement graph algorithms and hardly optimize for computations on sparse arrays. Recent work explores graph and relational workloads on tensor computing systems, for example, PyTorch, and these works produce high interest within the community. ArrayDBMSs have an exciting opportunity to join this novel trend.